Welcome to Orbit Observer. It's lovely to have you here tonight. Wherever you are right now, settle in. Maybe you're under a heavy blanket with the lamp still glowing soft and yellow in the corner. Maybe you're on a train, watching the dark slide past the window. Maybe you're on a couch or in a bed that isn't quite yours, in a city far from where you were born. It doesn't matter. You found your way here to this quiet little corner of the night, and that's enough. So tell me, before we drift off together, where in the world are you watching from tonight? What time is it in your part of the sky? I always like to imagine all of you scattered across the planet, eyes half closed, all listening to the same slow voice. There's something gentle in that. A lot of small windows, all lit up against the dark. And if you enjoy these slow journeys, if you'd like more nights like this one, a quiet like and a subscribe really does help this sleepy little channel keep going. Small creators like me genuinely rely on it. It's the soft push that keeps the lights on up here in orbit. And to those of you who already subscribed, who come back night after night, thank you. Truly, you're the reason I keep watch. Now here's my one little promise to you, the same one I always make. I'll try not to make this so interesting that it keeps you awake. But if it does, if you find yourself a little too curious to drift off, well, at least you'll have learned something. A fair trade, I think. And if you drift off long before the end, that's perfectly fine too. The ideas will still be here. The planet we're going to visit tonight has waited 4.5 billion years. It can wait for you to wake up. So let go of the day, let your shoulders drop. There's nothing you need to hold on to right now. We're going to move slowly, softly, one strange thing at a time. And you don't have to grasp every detail. You don't have to remember any of it. Just let the words wash over you like a warm current and let me do the steering. Tonight, we're going to a place that from up here looks like the most beautiful thing in the night sky. Look up sometime just after sunset or just before dawn and you'll see it. A single point of light, brighter than anything else out there except the moon. So bright that it can cast a faint shadow on a dark night. So bright that if you know exactly where to look, you can sometimes find it in broad daylight, a tiny silver pinprick against the blue. The ancient peoples watched it too. They saw it glowing in the morning and glowing in the evening, and for a long time they thought it was two different things. A morning star and an evening star. Two separate lights, two separate stories. It took them ages to realize it was one and the same, one world playing both parts, coming and going. That world is Venus. And it is, by almost every measure we can take, the closest thing Earth has to a twin. But I'm getting ahead of myself. Let me start with the thing that puzzled me the first time I really understood it. The thing that once you see it, you can't quite unsee, because it breaks a rule you've believed your whole life without ever really thinking about it. You know that the sun is hot. You know that the closer you stand to a fire, the warmer you feel. Step toward the flames and the heat rises on your face. Step back and it fades. This is one of the most basic, bone-deep truths we carry around. Closer to the heat means hotter. Farther away means cooler. It's so obvious it barely feels like a fact at all. It just feels like the way things are. So let's hold that thought and let me introduce you to the planet that sits closest to the sun, Mercury. The little scorched world nearest to the fire with barely anything between its rock and the full glare of our star. You'd expect Mercury to be the hottest place in the whole solar system, wouldn't you? It's standing right up against the flames, and in a way, you'd be right. On the day side of Mercury, where the sun beats straight down, the temperature climbs to around 430 degrees Celsius. That's hot enough to glow, hot enough to melt all sorts of metals, a genuine furnace. But here's the first strange thing about Mercury. It has almost no atmosphere, no blanket of air wrapped around it, nothing to hold the heat in. And so the moment Mercury turns its face away from the sun into the long dark of its night, all that heat just leaks away into space. There's nothing to keep it, nothing to tuck it in. And the temperature on the night side of Mercury plummets all the way down to around minus 180 degrees Celsius. Cold enough to freeze almost anything you can name. So Mercury is a world of violent extremes, roasting on one side, deep frozen on the other, swinging 600 degrees between day and night because it has no blanket of air to even things out. Right up against the fire, and it still can't hold the warmth. Now keep that picture in your mind, the little planet nearest the sun, swinging wildly between scorching and freezing. And let's step back. Let's move farther away from the sun, out past Mercury, to the second planet, to Venus. Venus orbits at a comfortable distance, tens of millions of kilometers farther from the sun than Mercury is. By our deep down rule, the closer to the fire rule, Venus should be cooler. It's standing farther back from the flames. It should feel the heat less, but it doesn't. Venus is hotter than Mercury. Hotter everywhere, and not by a little. The surface of Venus sits at a steady temperature of around 465 degrees Celsius. Let that number settle for a moment. 465 degrees, that's hotter than the blazing day side of Mercury, the planet that's practically touching the sun. And here's the part that I find almost unbelievable, the part that makes it stranger still. On Venus, that heat doesn't swing, it doesn't drop at night, it doesn't cool toward the poles. Day side, night side, equator, near the poles, it's all the same. Around 465 degrees, give or take just a few degrees everywhere, all the time. Think about how odd that is. On Earth, the desert bakes by day and chills by night. The poles are frozen while the tropics sweat. There's variety, there's a rhythm, there's a difference between noon and midnight, between Cairo and the Antarctic. But on Venus, there's none of that. Step anywhere on the entire planet, any hour, and you'll find the same relentless, even heat. A world held at one single temperature, like a room with the thermostat jammed and welded into place. A steady, all over 465-degree oven that never opens its door. And how hot is that, really, in terms you can feel? It's hot enough to melt lead. Pour a block of lead onto the surface of Venus, and it would slump and run like candle wax. It's hot enough to melt zinc, hot enough to melt tin, the metals we think of as solid, dependable, the stuff of pipes and coins and soldered joints. On Venus, they'd flow like water in a gutter. The whole surface of the planet is, in a sense, an oven set hot enough to liquefy metal and held there forever. So now we have a real puzzle, don't we? A genuine, beautiful little knot to untie before sleep. The planet closer to the sun is cooler. The planet farther away is hotter. The closer to the fire rule, the one we never questioned, just broke right in front of us. The distance to the sun is not the answer. Something else is keeping Venus that hot. Something is doing the work that distance can't explain. And here's where it gets stranger still. Because the first thing you might guess is also wrong. You might think, well, maybe Venus is just soaking up enormous amounts of sunlight. Maybe it's drinking in the sun's energy more greedily than anywhere else, and that's why it's so hot. But it's the opposite. Venus is wrapped completely, head to toe, in a thick deck of clouds. Not little wisps like the ones drifting over your house tonight. A total, unbroken, planet-wide shroud. You cannot see the surface of Venus from space. Not with your eyes. It's hidden under a featureless pale yellow veil, smooth and bright and blank, like a pearl, like a covered lamp. And those clouds are mirrors. they are extraordinarily good at bouncing sunlight straight back into space. Venus reflects roughly 75% of all the sunlight that reaches it. 3/4 of the sun's light just bounces off the top of those clouds and goes right back out into the dark, never reaching the ground at all. That's why Venus is so dazzling in our sky, by the way. That brilliant evening star, that morning star. It's so bright because it's such a good mirror, throwing the sun's light back at us across the void. Which means that down at the actual surface of Venus, beneath all that cloud, it's surprisingly dim. The light that finally filters through to the ground is less than half of what reaches the surface of Earth. Picture an overcast, gloomy afternoon, the kind where the light is flat and orange and heavy, where you might switch on a lamp at 3 in the afternoon. That's roughly how bright it is on the floor of Venus, dim, muted, a perpetual dull orange dusk. So sit with the strangeness of that for a moment here in the quiet. We have a planet that's farther from the Sun than Mercury. A planet that reflects 3/4 of the sunlight that hits it. A planet where less than half the remaining light even reaches the ground, where the surface sits in a dim orange gloom. By every measure of how much sunlight is getting in, Venus should be cool. It should be a mild, shadowed world. And instead, it's the hottest surface of any planet in the entire solar system, hot enough to melt lead, evenly everywhere, forever. So what on Earth, or rather, what on Venus, is doing this? The answer is the air. It's all in the air. And to understand it, we have to slow down and look at what that air is actually made of, and then at one very particular, very simple trick that it plays with light and heat. So let's go gently into it. No rush. This is the heart of the whole mystery, and it deserves to be told slowly. The atmosphere of Venus is almost entirely one single gas. Carbon dioxide, the same gas you breathe out right now with each slow breath in the dark. The same gas that fizzes in a bottle of soda, that hangs invisible around a dry ice fog. On Venus, that gas, carbon dioxide, makes up about 96.5% of the entire atmosphere, almost all of it. The little that remains is mostly nitrogen, a few percent, with traces of other things. But for our story tonight, you can picture the air of Venus as essentially one thing, thick and heavy and everywhere, carbon dioxide. And here is the simple, quiet trick that this gas plays. This is the whole secret, and it's gentler and stranger than you might expect. Sunlight, the light pouring out of the sun, comes mostly as visible light, the kind of light your eyes can see, the warm and golden kind. And carbon dioxide, it turns out, doesn't mind visible light at all. Visible light passes right through it, easily, without much trouble. So when the sun's light comes down toward Venus, the part of it that makes it past those mirror-bright clouds anyway, the carbon dioxide lets a good deal of it slip through. The light reaches the ground absorbs it. And just like a stone wall that's been sitting in the sun all afternoon, the warmed ground begins to give that energy back. It radiates heat. But here's the catch, here's the turn. The heat that the ground gives off isn't visible light anymore. It's a different kind of light, a slower, deeper kind that your eyes can't see, called infrared. You actually feel infrared all the time. It's the warmth you feel coming off a radiator or off a person standing close to you in the cold, even without touching them. That invisible glow of warmth, that's infrared. And carbon dioxide, which let the visible sunlight pass right through so easily, is almost completely opaque to infrared. It blocks it, it catches it. The heat radiating up from the ground tries to escape back out into space, the way it does on Mercury with its empty sky. But on Venus, the carbon dioxide is in the way. It grabs that outgoing heat and holds it, it traps it. The warmth comes in as visible light easily, and then it tries to leave as infrared and can't get out. So the heat builds and builds and builds. The sun keeps delivering a little energy through the clouds each day, and the carbon dioxide keeps refusing to let that energy escape back into space, and the warmth has nowhere to go but to accumulate day after day, year after year, century after century, until the whole planet is saturated with trapped heat all the way down. This is what we call the greenhouse effect. It's the same basic principle as a real greenhouse or a car left in a parking lot on a summer day. Light gets in easily, warms everything up, and then the heat finds it much harder to get back out, so the inside grows far hotter than the air outside. And Venus has the strongest greenhouse effect in the entire solar system, by far. Nothing else comes close. That ocean of carbon dioxide blanketing the whole planet traps so much heat that it raises the surface temperature by something like 500 degrees Celsius above what it would otherwise be. 500 degrees of trapped warmth. Without that atmosphere, Venus would be a cool, dim, unremarkable world. With it, Venus is a furnace that never goes out. And now finally, the whole puzzle clicks into place, doesn't it? Now you can see why Venus is hotter than Mercury, even though it sits farther from the Sun. Mercury has no blanket. The heat reaches it and then leaks straight back out into the dark, which is why its night side freezes. But Venus is wrapped in the thickest, most heat-greedy blanket of any planet we know, and it simply refuses to let go. The distance to the Sun was never the answer. The answer was the air, the blanket, the trap.
And that even all over temperature, the 465 degrees that's the same at the pole as at the equator, the same at midnight as at noon. That makes sense now too. That dense, heavy atmosphere is so good at holding and moving heat around that it smooths everything out like a thick stew that's the same temperature throughout the pot no matter where you dip the spoon. There are no cold spots on Venus, no shaded refuge, no cool night, no frozen pole.
The blanket covers everything completely and holds it all at the same lethal warmth. But the heat, as terrible as it is only one of the ways that Venus would kill you. There are at least two more, and they're happening at the very same moment, and I want you to feel all three of them stacked together because it's the combination that's so staggering. Let's talk about those clouds again, the bright, mirror-pale clouds wrapped around the whole planet. From a distance, they look soft and serene, like cream, like the surface of a pearl. But they are not made of water, the way the clouds drifting over your roof tonight are made of water. The clouds of Venus, hanging in great decks roughly 48 to 70 kilometers above the surface, are made largely of sulfuric acid, droplets of acid, the kind of acid that here on Earth we keep behind thick glass and warning labels, the kind that eats through metal and burns skin on contact. On Venus, it falls as a permanent haze, a sky full of acid, drifting and recycling in those endless pale clouds. So the same beautiful veil that makes Venus the brightest jewel in our evening sky is, up close, a sky of acid. And then there's the third thing, the pressure. And this one is harder to picture, so let's take it slowly, because I think it's the one that truly brings home what it would mean to stand on Venus. The atmosphere of Venus isn't just hot and acidic, it's heavy, enormously, crushingly heavy. All that carbon dioxide piled up in a thick column from the surface to high above presses down with tremendous force. The pressure at the surface of Venus is about 92 times the pressure you feel right now, sitting wherever you are at sea level on Earth. 92 times. That number is hard to feel, so let me give you something you can feel. You know how, when you dive down into deep water, your ears begin to ache? And the deeper you go, the more the water seems to press in around you from every side. That's pressure. The weight of all the water above you pushing in, while the pressure on the surface of Venus is the same as the pressure you'd feel if you were standing about 900 meters underwater. 900 meters. That's roughly 3,000 feet below the surface of the ocean, far, far deeper than any free diver has ever gone, deeper than sunlight can reach, a crushing black depth where the water would squeeze the breath out of you. That is the weight of the air on Venus, pressing down on the ground, on the rocks, on air, anything that dared to stand there. So now let's stack all three of them together, the way Venus would deliver them, all at once, in the same instant. If you could somehow stand on the surface of Venus, and you couldn't, not for a moment, but imagine it, you would be crushed by a pressure like the deep ocean, squeezed from every direction by the sheer weight of that thick carbon dioxide air. At the very same time, you would be roasting in heat, hot enough to melt lead, your whole body baking in an oven that never cools. And on top of all that, you'd be soaking in an atmosphere laced with sulfuric acid, chemically burning even as you were crushed and roasted and burned all at once, all in the same breath you'd never get to take. There is no place in the solar system more thoroughly, completely, relentlessly hostile to anything like us than the surface of Venus. And this is exactly where most stories about Venus begin and end. This is the picture nearly everyone paints: the hellscape, the acid clouds, the lead-melting heat, the crushing dark, the planet that would kill you 100 different ways before you finished a single thought. And then the story stops there, satisfied, as if that's all there is to say, as if Venus is simply a horror, a dead furnace, a closed case, the twin that died. But that's not where our story ends tonight. That's barely where it begins. Because I've told you only one half of the strangeness, and it's the lesser half. The greater strangeness is this crushing, roasting, acid-soaked furnace, this planet that looks for all the world like a corpse, a place where nothing could ever happen, where everything has surely long since burned to stillness. This furnace is not dead, not in the way you'd think. Underneath that smooth, blank, mirror-bright veil, something is still moving. Something is still happening, right now, today, while you lie here in the dark. There are things shifting and stirring on the surface of Venus, and we have caught them in the act. We have actual physical proof that sat hidden and unnoticed for 30 years before anyone realized what they were looking at. That Venus is still, in a very real and astonishing sense, alive. And there's more than that, gentler still and stranger still, because before Venus became this furnace, before the air turned to a blanket of fire, the evidence suggests that Venus and Earth were not just twins in size and weight. They may have been twins in something far more precious. There are fingerprints written into the chemistry of that murderous air that hint Venus once had oceans, real oceans, liquid water lapping on shores for perhaps 2 billion years, a near identical sister to our own gentle blue world, possibly mild, possibly wet, possibly, and here we have to be very careful and very honest, possibly a place where the story could have gone a different way entirely. So how does a world that may have had oceans for 2 billion years become an oven that melts lead? How do two planets start out as near-perfect twins, the same size, the same weight, the same basic ingredients, born side by side from the same cloud of dust around the same young sun? And then one of them stays a soft blue world full of life, while the other turns into the most lethal surface we know? What broke the twin? And if Venus is still moving, still changing, still alive in that strange geological way, Does that mean the breaking isn't finished? Does that mean we're watching a disaster that is still very slowly unfolding? These are the questions we're going to drift through together, slowly, one soft step at a time. We'll find the ghost of that lost ocean, written in a single number, hidden in the chemistry of the air. We'll walk gently through how a world can boil its own oceans away and never get them back. We'll come, at last, to the volcano that changed shape in 8 months and sat unnoticed in an old archive for 3 decades, the discovery that turned Venus from a corpse back into a living world. And we'll meet the spacecraft with their strange and lovely names that are right now being built and prepared to fly across the dark to Venus in the years ahead to finally answer the oldest question we have about our broken twin. Why did it die when ours did not? But all of that is for the parts still ahead of us. For now, just hold the picture I've given you. A pale, beautiful point of light in your evening sky. The brightest thing up there after the moon. A world almost exactly the size of our own. And beneath its mirror-bright veil, a furnace hot enough to melt lead, crushing as the deep ocean, soaked in acid, and yet somehow, against everything you'd expect, not quite dead. Let that settle. There's no need to hold on to any of the numbers. Let the 465 degrees, the 92 times the pressure, the 96% carbon dioxide, let all of it loosen and float away if it wants to. What matters is the feeling of it. A twin of our own world, so close in size and weight and birth, that went so terribly, completely wrong. And the quiet, astonishing fact that it may still be going wrong, right now, tonight, while you rest. So breathe slow. Let the warmth of your blanket be the only warmth you think about. We're a long way from the surface of Venus, you and I. Safe up here, watching from a gentle distance, far from the acid and the crushing dark. And we have a long, soft journey still ahead of us, deeper into the mystery of the twin that broke. So stay with me if you can. And if you can't, if sleep is already reaching for you, pulling you down into the dark and the quiet, then let it. Let go. The lost ocean, the boiling away, the volcano hidden in the old images, the ships being built to fly there, all of it will still be here, waiting, patient as the stars, just as it has waited for 4.5 billion years. Welcome to Orbit Observer. It really is lovely to have you here tonight, wherever you are. Maybe you're lying in the dark already, the lamp off, the day finally behind you. Maybe there's a little light still on somewhere, a phone face down on the blanket, the soft hum of a room settling into stillness. Wherever you are in the world tonight, I'm glad you found your way up here. And before we drift any deeper, just a small, quiet thing. If you enjoy these slow journeys through the sky, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. And to those of you who've already subscribed, who come back night after night, thank you. Truly, you're the reason there's a voice up here at all. So tell me before you fade, where in the world are you watching from tonight? What time is it in your corner of the dark? I love imagining you out there, scattered across the whole turning planet, all of us looking up at the same handful of lights. Now, settle in. There's nothing you need to do from here, nothing to remember, nothing to follow closely. If you drift off halfway through, that's not a failure, that's the whole point. The ideas will keep. Venus has waited 4.5 billion years. It can wait for you to wake up. So let's go back to the strangeness I left you with, because here's the thing that breaks your intuition. Gently, right at the start. You'd think the closer a world sits to the sun, the hotter it would be. Simple. Obvious. And mostly that's true. Mercury huddles right up against the Sun, closer than any other planet, bathing in that ferocious light. And on its day side, Mercury roasts, around 430 degrees Celsius, hot enough certainly. But then Mercury turns, and its night side falls away into the cold. With no real air to hold the heat, all that warmth simply bleeds away into space. And the temperature plunges down to nearly minus 180 degrees, from a furnace to a deep freeze, depending only on whether the Sun is shining on you. Now hold Venus beside it. Venus sits much farther out, tens of millions of kilometers farther from the Sun than Mercury. By every easy assumption, it should be cooler, calmer, a milder world. It isn't.
Venus is hotter than Mercury, not sometimes, everywhere, all the time. A steady 465 degrees, give or take, across the entire planet. The day side, the night side, the equator, right up near the poles. Barely a few degrees of difference between any of them. There's no cool place to hide on Venus, no shaded valley, no long polar night that brings relief. The whole world sits at one even, lethal temperature. Hot enough to melt lead, hot enough to melt zinc,
hot enough to melt tin and let it run like water. A planet farther from the fire, somehow burning hotter than the one beside it. And once you really feel how strange that is, you can't unfeel it. It shouldn't be possible. So what's going on? The easy answer would be distance. But distance, as we've just seen, points the wrong way. So it can't be that. In fact, here's something that makes it even stranger. Venus barely lets the sunlight in. Picture that mirror-bright veil again, the pale glow that makes Venus the brightest light in your evening sky. That brightness isn't warmth pouring in, it's sunlight bouncing off. Venus is wrapped in a thick, unbroken deck of clouds, drifting somewhere between 48 and 70 kilometers above the surface. And those clouds reflect about 75% of the sunlight that reaches them straight back out into space. 3/4 of it turned away at the door, so the surface of Venus actually receives less than half the sunlight that touches the surface of Earth. Less than half. Down there, beneath all that cloud, it's a dim, heavy, reddish gloom, far less sunlit than a clear afternoon on your own world. And yet it's roasting. A planet that turns most of its light away, sitting in shadow under its own clouds, still hotter than anything else in the inner solar system. So if it isn't distance, and it isn't even the amount of sunlight getting in, then what is doing this? The answer is in the air itself. And it's the same word you've heard before, only here it's turned all the way up, past anything Earth has ever known. Venus's atmosphere is almost entirely carbon dioxide, 96.5% of it. Carbon dioxide, that quiet gas, the one you breathe out, the one that lingers in our own conversations about a warming Earth. On Venus, it isn't a trace. It's nearly the whole sky. And carbon dioxide has a peculiar habit. It lets sunlight through easily. Visible light slips right past it, down through the clouds, and warms the rocky ground below. But when that warmed ground tries to send its heat back out, back up and away the way it should as infrared, as that invisible glow of warmth, the carbon dioxide won't let it pass. To outgoing heat, it's nearly opaque. A one-way door, light comes in, warmth tries to leave, and the air closes around it and holds it down. That's the greenhouse effect, and on Venus it's the strongest in the entire solar system, strong enough to lift the surface temperature by roughly 500 degrees above what it would otherwise be. 500 degrees of trapped, accumulated, inescapable heat. Without that thick blanket of carbon dioxide, Venus would be a far gentler place. With it, the planet became a furnace that can never cool down because the heat simply has nowhere left to go. And then, as if that weren't enough, there's the weight of it. All that air doesn't just trap heat, it presses. The atmosphere on Venus is so thick, so dense, that the pressure at the surface reaches about 92 times the pressure you feel right now, lying safe in your bed. 92 times. Try to imagine that. The easiest way is to think of water. You know how, even a few meters down in a pool, you can feel the pressure pushing on your ears. Now go deeper. The pressure on the surface of Venus is roughly what you'd feel standing 900 meters underwater, 3,000 feet beneath the waves, in the lightless deep, with the whole crushing weight of the ocean stacked above you. That's just the air. That's just standing there. So picture, for one strange moment, what it would actually be to stand on Venus. You'd be crushed by that immense ocean-deep pressure. You'd be roasted by heat that melts lead. And you'd be burned, all the while, by clouds made not of water, but of sulfuric acid, crushed and roasted and dissolved all at the same instant. No world we've ever found is so thoroughly, so completely hostile to anything soft and alive. And yet, here's where it gets strange again. And this is the thing I really brought you up here to tell you. This furnace isn't a corpse. For a long time, we thought of Venus as a dead world, a horror story with an ending, hot, crushing, finished. But that picture is wrong. Because somewhere down there, beneath all that acid and weight and trapped ancient heat, we caught something moving. A volcano, caught in the very act of erupting, hiding for 30 years in plain sight. But to understand how we found it and why it changes everything, we have to go back to the ships we sent. So stay with me a little longer. And before we can understand what we found, before we can talk about what's still moving down there on that burning world, we have to understand just how closely Venus resembles the world you're lying on right now, because this is the part that stops people. This is the part that makes the whole story strange in a different, quieter way. Venus is not just sort of like Earth. It's not a vague cosmic cousin, a planet that happens to be nearby and roughly round. The resemblance is specific, and it's almost eerie. Let's go through the numbers slowly. There's no rush. Earth's diameter from one side to the other is about 12,742 kilometers. Venus's diameter is about 12,104 kilometers. That's roughly 95% of Earth's size. If you placed a model of Venus next to a model of Earth and stepped back a few meters, you would have to look very carefully to tell which was which. They are nearly the same ball of rock. The mass is close too. Venus weighs in at about 81.5% of Earth's mass, not identical, but in the same neighborhood. And when you stand on Venus's surface, the pull you'd feel beneath your feet is that familiar, grounding downward tug. Would be about 90% of what you feel right now. 9/10 of a G. Close enough that if you closed your eyes and ignored everything else, ignored the crushing pressure, the heat, the acid, your body would feel almost at home. In every number that matters to a geologist or a planetary scientist trying to understand how a world is built, Venus and Earth are essentially the same. Same size, same mass, same density, same general composition of rock and iron. In the whole solar system, no other world comes close. Mars is too small. Barely half Earth's diameter, 1/10 of its mass, with gravity so weak you'd bounce with every step. Mercury is smaller still, more metallic oddity than sibling, and the gas giants are in an entirely different category, enormous, and made mostly of swirling hydrogen with no solid surface to stand on at all. Venus is the most Earth-like planet we have ever found anywhere. That's not sentiment, it's measurement. So when we call Venus Earth's twin, we mean it with precision, and that's exactly what makes the story so strange, because a twin shouldn't end up this way. When you hear about two people born to the same parents, raised in similar conditions, you expect them to share some general arc. Same start, similar story. You don't expect one of them to be living a calm, comfortable life and the other to be standing in a furnace at 465 degrees, crushed under the weight of an ocean, dissolved in acid. That kind of divergence demands an explanation. Something happened to Venus. Something went deeply, catastrophically wrong. But here's what makes the story even more haunting. The evidence suggests Venus didn't start that way. Close your eyes for a moment, or just let them rest. Picture Venus not as it is now, not the pale, featureless, furiously bright disk we see in the evening sky, but as it may have been long, long ago in the first chapter of the solar system's life. The best models we have, including work published in 2016 by Michael Way and his colleagues at NASA's Goddard Institute for Space Studies, NASA JPL in New York, suggest that in its early history, Venus may have had a stable climate, not just tolerable, potentially habitable, with liquid water on its surface, with oceans, with temperatures that by the broad standards of life as we understand it, could have been reasonable, warm maybe. Not so different from a very warm day on Earth. And this isn't fringe speculation. It comes from climate modeling that takes Venus's actual orbital parameters and early solar conditions and asks, what would Venus have looked like if it had started with water before the sun grew brighter? The models say it could have been fine, it could have been stable for a long time. How long? Way and his team modeled scenarios in which Venus maintained habitable conditions for up to 2 or 3 billion years. 2 to 3 billion years. To put that in perspective, complex animal life on Earth only began in the last 500 million years or so. A world can do a very great deal in 2 billion years. Life on Earth had been going for billions of years before anything more complex than a single-celled organism existed. 2 to 3 billion years of habitable Venus is, in principle, an enormous amount of time for something to start. Now, we don't know if life ever started on Venus. We have no evidence either way. But the point isn't life. The point is this. The twin was once, possibly, a world that could have supported it. The furnace we see today had a different face once, a wetter face, a gentler one. Something broke it. And the thing that broke it left a fingerprint. A chemical fingerprint pressed into the atmosphere itself that we can still read today, if we know how to look. Here's how it works. Water, ordinary water, the kind in your glass, the kind that falls as rain, is made of 2 hydrogen atoms bonded to 1 oxygen atom. You already know this. H2O, what you might not think about is that hydrogen itself comes in more than one flavor. The common kind is just a single proton with an electron. Lightweight, simple. But there's a heavier version of hydrogen called deuterium. Same single proton but with a neutron added. Twice the mass of ordinary hydrogen but chemically almost identical. Water can be made with either kind. Now here's the crucial thing. When water gets into an upper atmosphere and sunlight breaks it apart, when ultraviolet radiation splits those H2O molecules, the hydrogen atoms that get released don't all escape at the same rate. The lighter ones, ordinary hydrogen, move faster and escape to space more readily. The heavier deuterium, because of its extra mass, is a little slower, a little harder for gravity to lose, so it tends to stay behind. What this means is that if a planet loses water to space over billions of years, the lighter hydrogen bleeding off, the heavier deuterium left behind, the ratio of deuterium to ordinary hydrogen in the remaining water or in the atmosphere will climb. The more water lost, the higher the ratio rises. The deuterium to hydrogen ratio is a kind of clock or a ledger recording how much water has been lost. And on Venus, that ratio is extraordinary. The deuterium to hydrogen ratio in Venus's atmosphere is roughly 100 to 150 times higher than Earth's, 100 to 150 times. That isn't a small difference, that's a screaming signal. It means Venus has lost an enormous amount of water over its history, so much water that the lighter hydrogen bled away in such quantities that what remained became grotesquely enriched in the heavy kind. The models suggest this could be consistent with Venus once holding something close to a global ocean. A shallow one, perhaps, but planet-wide, a world covered in water. That ocean is gone now, not a drop left on the surface, not even in the clouds, which are acid, not water. But the ratio remains, written in the air, like an inscription in stone that long outlasted the civilization that carved it. Venus once had water. We can read it in the chemistry, even though the water itself is gone. So let's follow the water. Let's walk very slowly through what probably happened, because this is the heart of the story, the moment the twin broke, and it deserves to be understood clearly. Start with a warmer world. Venus, in its younger days, perhaps 2 or 3 billion years ago, possibly still with oceans, and the Sun slowly over millions and billions of years doing what it has always been doing, getting brighter. The Sun is not a fixed, constant candle. It's been gradually, steadily brightening over its lifetime. In the early solar system, it was perhaps 30% dimmer than it is today. Over billions of years, it has grown more luminous. And at some point, either because of the brightening Sun crossing a threshold, or because of a volcanic catastrophe releasing huge amounts of CO2 into the air, or some combination of the two, Venus began to warm beyond what it could handle. Now at first, this sounds manageable, a few degrees warmer, what's the harm? But here's the catch, and it's a devastating one. As temperatures began to rise, the oceans began to evaporate more quickly. More water vapor rose into the air, and water vapor, ordinary water vapor, the kind of humidity that makes a summer day feel sticky, is itself a powerful greenhouse gas. Not as powerful as CO2, but significant. So as the oceans evaporated, more water vapor entered the atmosphere, and more water vapor in the atmosphere trapped more heat, and more heat meant more evaporation, which put more water vapor in the atmosphere, which trapped more heat. A loop, a feedback loop, each turn of the wheel making the next turn faster. This is what climate scientists call the runaway greenhouse effect. Not a greenhouse effect that gradually warms and then stabilizes, a greenhouse effect that, once triggered past a certain threshold, has no natural stop. The warming feeds itself, the evaporation feeds the warming feeds the evaporation, and there is no break. The oceans got hotter, they evaporated faster, more water vapor poured into the sky, temperatures climbed further, eventually, and this process would have taken a very long time, millions of years perhaps, but eventually, the oceans boiled away entirely, not a gradual drying out like a lake in a drought, a full, wholesale loss of the surface water. And then with all that water now vapor in the upper atmosphere, the sun's ultraviolet radiation went to work. Sunlight, specifically the ultraviolet end, has enough energy to split water molecules apart. It broke the H2O in Venus's high atmosphere into hydrogen and oxygen. And the hydrogen, light, fast-moving, now free, escaped, drifted up and away into space, gone. The oxygen mostly went into oxidizing surface rocks. It got swallowed into the ground. And the water was simply gone, not transformed, not recycled, gone. The loop had run to completion and the result was permanent, irreversible. There was no ocean to rebuild from, no reservoir to refill. The water had left the planet atom by atom, hydrogen drifting away into the void, and Venus would never get it back. This is what irreversible means in planetary terms. It's not a metaphor. Once the water is gone, it's gone. The chemical fingerprint, all that excess deuterium in the atmosphere, is all that remains. And there's another piece of this story, another mechanism that made the water loss faster and more complete than it might have been otherwise. Earth has a global magnetic field. You can't see it or feel it, but it's there. Generated by the motion of molten iron in Earth's outer core, a churning dynamo that wraps the whole planet in an invisible magnetic shield. And this shield does something very important. It deflects the solar wind. The solar wind is a constant stream of charged particles, i.e. protons and electrons, blasting outward from the sun at hundreds of kilometers per second. When these particles hit an unshielded atmosphere over millions and billions of years, they can strip it away. They hit the upper atmosphere, they excite and energize ions, they knock particles out into space. It's a slow process, but it's relentless. And over geological timescales, it matters enormously. Venus has no global magnetic field, not even a weak one. Why it lacks one is still not entirely settled. It may be related to the slow rotation rate, which affects how a planetary dynamo can form. Whatever the reason, Venus's atmosphere is directly exposed to the solar wind with nothing to deflect it. We know this because we've measured it. The European Space Agency's Venus Express mission, which orbited Venus from 2006 to 2014, directly detected ions, charged particles from Venus's own atmosphere, being swept away downstream by the solar wind. You could measure it happening in real time. ESA's instruments watched hydrogen and oxygen ions being dragged out into space. The loss was going on right now, not just in the ancient past. NASA's Messenger spacecraft, primarily a Mercury mission, also made flybys of Venus and contributed to the picture of an unshielded world, its atmosphere being slowly peeled away. So here is the situation Venus found itself in, with no magnetic field and a runaway greenhouse already in progress. The solar wind hammered the upper atmosphere directly. Lighter atoms, hydrogen especially, were stripped away more efficiently. The very water vapor that had risen during the runaway process was being shredded and its hydrogen components blown off into space. The two mechanisms, the thermal runaway and the solar wind stripping, worked together, reinforcing each other, making the loss of water faster and more thorough than either process would have been alone. The result is the dry, scorched, dense, CO2-choked world we see today. Now this is the part I want you to sit with for a moment, because it's the cautionary core of this whole story. Let's talk about carbon. Carbon dioxide, CO2, is the villain of Venus's story. 96.5% of Venus's atmosphere is CO2, and that CO2 is responsible for the roughly 500-degree boost it applies to the surface, so the most powerful greenhouse warming of any planet in the solar system. The furnace is made of trapped carbon, but here's the thing, Earth has enormous amounts of carbon too. We are not a carbon-poor planet. In fact, geochemists who study this believe that Earth and Venus probably started with very similar total inventories of carbon, similar amounts of carbon-bearing material delivered during the formation of the solar system and the early period of bombardment, when the same mix of rocky and icy debris that built Venus also built Earth. Same starting hand. So where is all of Earth's carbon? It's not in the air. If you look at Earth's atmosphere, CO2 makes up less than half of 1%, a tiny trace compared to Venus's nearly complete blanket of the stuff. But the carbon didn't just disappear, most of it is locked away in rock. When it rains on Earth, and it rains on Earth because Earth has oceans, liquid water, cycling through the atmosphere, that rain is very slightly acidic because it picks up CO2 from the air and carries it down as carbonic acid. This weak acid falls on rocks. It reacts with silicate minerals in those rocks, and the products of that reaction, calcium carbonate, magnesium carbonate, wash into the rivers and eventually into the ocean. In the ocean, they get taken up by living things that build shells and skeletons out of calcium carbonate. And when those creatures die, their shells and bones sink to the ocean floor and get buried, locked away in what becomes limestone and chalk and marble. Carbon taken out of the air, pressed into stone. This process, the carbon silicate cycle, requires liquid water. It requires rain. It requires rivers. It requires oceans for things to accumulate in. And it requires the slow churn of plate tectonics to bury the rock and, over geological timescales, to bring some of it back up in volcanoes, releasing a little CO2 back into the air, keeping the cycle cycling rather than simply draining away all the carbon forever. Earth's carbonate rocks, its limestone, its chalk, represent billions of years of CO2 that was once in the atmosphere, pulled down, locked away, stored. The White Cliffs of Dover are, in a sense, ancient air, compressed, mineralized, and pressed into the coastline. Venus has none of this. No liquid water means no rain falling on silicate rocks. No carbonic acid washing into rivers. No oceans for carbonates to accumulate in. No plate tectonics to bury and recycle in the same way. No living things building shells. The carbon had nowhere to go. It stayed in the air, all of it. 96.5% of an atmosphere made almost entirely of what on Earth has been tucked away into stone. And here's the number I want you to remember, because it's the one that makes this feel personal. If you could take all of Earth's limestone, all the carbonates, all the buried ancient CO2 that's been patiently tucked into rock for billions of years, and release it back into the atmosphere at once, Earth's atmosphere would look almost exactly like Venus's. Same pressure, same composition, same temperature. Earth's carbon isn't absent, it's just hiding. It's hiding in the rocks, held there by liquid water and rain and the slow chemical breathing of a living planet. Take the water away, and the rocks can no longer hold it. Take the oceans away, and there's nowhere for the carbon to go. The air becomes Venus's air. The surface becomes Venus's surface. The same starting hand, a different outcome. And the difference came down to one thing: water. Whether you kept it or lost it. Whether your magnetic field held long enough, whether the sun's brightening came too fast, whether the volcanic feedback tipped before the water could lock the carbon away. Venus lost the coin flip. Or maybe it never had the same coin to flip. And that's the thought worth carrying into sleep tonight if you're still with me. Not as a thing to worry about, just as a thing to understand. Venus is not a cautionary tale from another world. It's a cautionary tale from a different version of this one. The same elements, the same chemistry, the same starting conditions. One of them found a stable equilibrium. Liquid water, plate tectonics, a carbon cycle, a magnetic field, life. The other tipped and fell and couldn't stop falling. But now, and this is where the story takes its turn, the turn I promised you at the beginning, I want to push back against the idea that the falling is finished. Because for a long time, that's exactly how we thought of Venus. A world that had fallen, past tense. A dead furnace, its geological story over, its surface baked and static and ancient. The kind of place where nothing changes anymore, where the story ended billions of years ago and all that's left is the aftermath. That picture, it turns out, is too simple. To understand why, you need to understand the Magellan spacecraft, because Magellan is where the real story begins. And it's also beautifully and almost improbably where the story was found. Magellan was a NASA mission launched in 1989. It reached Venus in 1990, and it spent 4 years, from 1990 to 1994, orbiting Venus and mapping its surface by radar. Radar, not cameras, because cameras can't see through the clouds. Venus's thick, permanent cloud decks block all visible light from reaching the surface. The only way to see what's down there from orbit is to bounce radio waves off it and read the echoes. the same principle as a ship's sonar reading the ocean floor. Magellan sent down radar pulses and listened for what came back, and from the echoes it built maps, extraordinarily detailed maps. By the time the mission ended, Magellan had mapped 98% of Venus's surface. It was a tremendous achievement. For the first time, we had a nearly complete portrait of the surface hidden beneath those acid clouds. We could see mountains and plains and craters and vast volcanic structures. We could see what Venus actually looked like, stripped of its featureless pale exterior. And then Magellan's mission ended, and the spacecraft itself was deliberately sent into Venus's atmosphere to burn up, a controlled descent to gather a few final measurements. And the data was archived. Thousands of radar images carefully stored, analyzed over the following years, and then left, as data tends to be in the archives, available, accessible, sitting there for about 30 years. And this is the thing that makes the 2023 discovery feel almost more like a detective story than a scientific paper. Because the finding didn't come from a new mission, it didn't come from a cutting-edge instrument or a freshly launched satellite. It came from someone sitting down with 30-year-old data and looking at it very carefully in a new way, with fresh eyes. Robert Herrick, a planetary scientist at the University of Alaska Fairbanks, and Scott Hensley, a radar expert at NASA's Jet Propulsion Laboratory in California, decided to go back into the Magellan archive. They were specifically looking for evidence of geologic change, for any sign that Venus's surface had shifted or moved during the time Magellan was taking its images. This sounds straightforward, but it isn't. The Magellan images, while remarkable for their time, were not designed to be compared to each other with this level of precision. The radar illuminated the surface from slightly different angles on different passes. The resolution, while impressive, had limits. Comparing two images of the same feature taken months apart and trying to determine whether the feature had changed was painstaking work, complicated by all the ways the images could look different, even if nothing on the ground had moved at all. Herrick, by his own account, spent a long time simply going through the images by hand. Not an algorithm, not automated detection software. Manually, looking. He was looking at a region around a volcanic structure called Maat Mons. Maat Mons is one of the largest volcanoes on Venus. A shield volcano, the kind built up over many eruptions into a broad, low, gently sloping mountain, similar in general shape to the Hawaiian volcanoes here on Earth. It sits near Venus's equator and rises several kilometers above the surrounding plains. It had been noticed in the Magellan data as a region of particular volcanic interest, with surface textures suggesting it might be geologically young. But there was no direct evidence at the time that it was currently active. Just the textures, just the hints. What Herrick found in the Magellan archive were two radar images of a volcanic vent, an opening in the ground, a collapsed depression through which lava can emerge, on the flank of Maat Mons. One image was taken in February of 1991. The other was taken 8 months later, in October of 1991. Both images showed the same vent, but the vent wasn't the same. In the February image, the vent was roughly circular. Its area was about 2.2 square kilometers, not large, but clearly defined. By October, 8 months later, the vent had changed shape. It was no longer circular. It had become irregular. Kidney-shaped is the description that appears in the paper, a lumpy, uneven outline, very different from the near circle in the earlier image. And it had grown. The area had roughly doubled to over 4 square kilometers, and on the flanks of the vent there appeared to be new material. Something that hadn't been there before, something that looked, in the radar returns, like a fresh lava flow. New rock poured out and solidified on the surface in the months between the two images. Robert Herrick and Scott Hensley published these findings in the journal Science in 2023, and the interpretation they offered was the straightforward one because it was the one that fit all the data. This vent had been the site of a volcanic eruption sometime between February and October of 1991. The vent had changed shape because volcanic activity had altered it from within. The new material on its flanks was fresh lava. Venus had been volcanically active during the Magellan mission, and no one had noticed because the images had been sitting in an archive waiting for 30 years. Think about that for a moment. The spacecraft that found the evidence was launched before the internet, before GPS became widespread, before the World Wide Web existed as a public tool. The images were taken when cassette tapes were still a common music format. The eruption happened, if it happened as interpreted, in 1991, and the confirmation, the close reading of the evidence, arrived in 2023. The volcano didn't know it was being observed, it didn't know it would be found, it just did what volcanoes do, and for 30 years, the proof of it sat in a database, compressed and patient, waiting for someone to look carefully enough. So let's set that remarkable discovery aside for a moment, not because it isn't important, but precisely because it is. And we'll come back to it. We'll let it sit in the back of your mind, quietly, the way a question does when you know the answer is coming, but you want to understand it properly first. Because to truly understand what it means that Venus is geologically alive, you need to understand what Venus actually is. Not what it feels like, not the heat, the acid, the crushing weight of the air, but what it is structurally in the family of planets. And to do that, we need to talk about the twin too. The word gets used loosely in popular writing about the planets. Venus is Earth's twin, the way two different colored cars of the same model might be called twins. Similar enough to share the name, different enough that no one would actually confuse them. But the twin comparison for Venus is something genuinely unusual. It is, in planetary terms, almost uncomfortably close. Venus's diameter is approximately 12,104 kilometers. Earth's is approximately 12,142 kilometers. If you do that division, you get about 95%. Venus is 95% of Earth's size, not roughly the same size, not in the ballpark, 95%. The mass is about 81.5% of Earth's, slightly less proportionally than the size comparison would suggest, because the two planets have slightly different internal compositions. And that mass difference translates into surface gravity. On Venus, you would weigh about 90% of what you weigh here. Not dramatically lighter, not noticeably lighter if you're honest, almost the same. In terms of bulk density, overall composition and position in the solar system, Venus is the most Earth-like planet we know of, not Mars, which is about half Earth's diameter and less than 11% of its mass, with a thin, cold atmosphere and no liquid water on the surface. Not any of the gas giants, which are barely comparable. Venus, the next planet inward, your nearest planetary neighbor. If you were designing a world that could host life as we know it, you'd probably start with something very close to Venus's raw numbers. And yet, here is where the story gets interesting, and where the science gets genuinely strange, because the evidence suggests that Venus didn't always look the way it does now. There is a ghost haunting this planet. Not a metaphorical one, a chemical one. Scientists have been able to measure the ratio of two forms of hydrogen in Venus's atmosphere, deuterium and regular hydrogen. These are both hydrogen atoms, but deuterium is the heavier version, carrying an extra neutron. When water vapor rises to the upper atmosphere, it can be split apart by sunlight. The resulting hydrogen atoms are light enough to escape into space. But here is the key: the lighter form of hydrogen, ordinary hydrogen, escapes faster than deuterium because it's less massive and therefore easier for the planet's gravity to lose. So if a planet has been losing water to space over a very long time, you'd expect the remaining hydrogen in its atmosphere to be enriched in deuterium. The heavier form accumulates as the lighter form bleeds away. The ratio becomes a fingerprint, a record. Venus's deuterium to hydrogen ratio is approximately 100 to 150 times higher than Earth's. 100 to 150 times. That number is not a curiosity. It is a chemical scar, the trace left behind by an enormous amount of water that used to be there and is no longer. The leading interpretation of this signature is that Venus once held a substantial amount of surface water, not puddles, not seasonal moisture, something closer to a global ocean's worth. The water is gone, but the ratio of what's left tells you it was there. In 2016, Michael Way at NASA's Goddard Institute for Space Studies led a team that took this line of evidence seriously and built a climate model around it. What they found is still, in some quarters, considered one of the more startling results in planetary science of the past decade. Their models suggested that Venus, with a slower rotation rate and a young sun slightly less bright than today's, could have maintained a stable climate with liquid water on its surface for something in the range of 2 to 3 billion years. 2 to 3 billion years. For perspective, complex multicellular life on Earth didn't appear until roughly 600 million years ago, and single-celled life had already been present for more than 3 billion years before that. 2 to 3 billion years of stable liquid water is an enormous amount of time. It is longer than the interval between the first appearance of bacterial life on Earth and the present moment. Now the Way 2016 modeling has uncertainties. It depends on assumptions about Venus's early rotation rate and cloud cover. It is a model, not a measurement, and models are only as good as their inputs, but it sits within a credible parameter space, and it is consistent with the deuterium fingerprint, which is a measurement. The two lines of evidence point in the same direction. Venus was, quite possibly, a world where life could have taken hold, and then something changed, and the change, once it began, was irreversible. This is the mechanism that planetary scientists call the runaway greenhouse, and it is worth walking through slowly because it is one of the more important processes in the solar system, not just for understanding Venus, but for understanding what Earth is and what it might become. It starts with heat. Just a little more heat than the planet is used to. This could come from a slowly brightening star. The Sun, like most stars, has been steadily increasing in luminosity over time, and the young Sun was perhaps 30% fainter than it is today. As Venus's sun brightened, the equilibrium that had kept the climate stable began to shift. The oceans, slightly warmer, began to evaporate more readily. More water vapor entered the atmosphere, and here is the critical step, the one that closes the trap. Water vapor is itself a greenhouse gas, a powerful one. As more water evaporated, the atmosphere trapped more heat. As the atmosphere trapped more heat, more water evaporated. More vapor, more warming, more vapor, more warming. The feedback loop had no natural break. On Earth, the carbon-silicate cycle, a slow geological process where CO2 is drawn down from the atmosphere, incorporated into carbonate rocks, subducted by plate tectonics and outgassed by volcanoes, acts as a thermostat, keeping temperatures within a range where liquid water is stable. But for that thermostat to work, you need liquid water to begin with. Water participates in the weathering reactions that pull carbon out of the air. Remove the water and the thermostat stops functioning. On Venus, once the oceans began to go, the system lost its ability to regulate itself. The evaporation continued, the warming continued. Eventually, the oceans didn't just evaporate, they boiled off entirely. Vast quantities of water vapor rose into the upper atmosphere, where ultraviolet radiation from the sun split the water molecules apart into hydrogen and oxygen. The hydrogen, light and fast, bled away to space. The oxygen largely reacted with surface rocks. The water was gone, permanently, irreversibly. There was no mechanism to bring it back. and all the CO2 that had been locked away in rocks, in what had once been ocean sediments, in carbonate minerals, stayed in the atmosphere, or was outgassed from the interior. Because without liquid water, without plate tectonics operating smoothly, without the carbon-silicate cycle running, there was nothing to take it back out. Venus, which had probably started with roughly the same total carbon dioxide inventory as Earth, now had essentially all of it in the air at once. Earth has the same amount of carbon. It is just not in the atmosphere. It is in limestone, it is in chalk, it is dissolved in the oceans, it is locked in the bodies of living things and in the fossil remnants of things that lived millions of years ago. The difference between Earth and Venus chemically is largely the story of where the carbon ended up. If you took all of Earth's locked carbon and released it into the atmosphere, Earth's air would begin to resemble Venus's. That is not a poetic comparison, that is roughly what the geochemistry suggests. This is the cautionary core of the Venus story. The thing that makes planetary scientists uncomfortable in a specific, productive way. Earth and Venus were dealt the same hand. One of them is where you are right now, under a blanket, drifting towards sleep. The other is a world where lead melts on the surface and the air itself is a slow acid. And running underneath all of this, contributing to the irreversibility, is one more absence worth noting. Venus has no global magnetic field. Earth's magnetic field, generated by the churning of its liquid iron outer core, acts as a shield, deflecting the solar wind, the constant stream of charged particles flowing outward from the sun. Without that shield, the solar wind interacts directly with the upper atmosphere. ESA's Venus Express spacecraft in orbit around Venus from 2006 to 2014 confirmed that Venus is actively losing atmospheric material to space even today, stripped away by the solar wind. The Messenger spacecraft, during its flybys of the inner solar system, contributed complementary measurements. The loss rate is not catastrophically fast by human timescales, but over billions of years it adds up. The absence of a magnetic field meant the solar wind had unobstructed access to Venus's upper atmosphere for essentially its entire history, gently stripping away lighter components, including, long ago, the hydrogen from what had once been water. The planet that may have had oceans lost its water through two routes simultaneously: the runaway evaporation that sent water vapor into the upper atmosphere to be split by sunlight, and the solar wind erosion that carried the resulting hydrogen away. Both processes required billions of years. Both processes required the absence of the safeguards that Earth still has. And here you are, lying on Earth, beneath Earth's magnetic field, inside Earth's carbon-silicate thermostat, with Earth's oceans still intact. That's not a small thing. There is a version of Venus that most videos never quite reach. The tour usually ends at the heat, the pressure, the acid. The litany of horrors stacked one on top of the other until the word hellscape arrives, right on schedule, and the credits roll. Venus as a closed case. Venus as a cautionary tale already told, already filed away. A world that burned itself to a cinder and has been sitting there, fixed and finished ever since. But that version of Venus is missing something important, something that nobody knew was hiding in an archive for 30 years. So let's stay with it a little longer wherever you are tonight, because the next part of this story is the one that changes the frame entirely. The spacecraft that gave us our best look at Venus was called Magellan, a NASA mission launched in 1989, arriving at Venus in 1990 and spending the next 4 years doing something the clouds had always prevented: mapping the surface. Not with visible light. The clouds block that, absolutely. But with radar. Magellan sent radar pulses down through 60 kilometers of sulfuric acid haze, and those pulses bounced off the surface and came back. And from the patterns of those echoes, scientists assembled a picture of what lay beneath. By the time the mission ended in 1994, Magellan had mapped roughly 98% of the entire Venusian surface. Mountains, plains, canyon systems, volcanic structures, all of it rendered in detail, finer than anyone had managed before. And then the data went into an archive. That's not a criticism. That's how science works. You collect what you can, you process what you can process with the tools you have, and you file the rest away for when better questions or better methods arrive. The Magellan data sat in storage through the 90s, through the 2000s, through the 2010s. Researchers dipped into it for various projects. But nobody in all that time had done something rather obvious and rather painstaking. Nobody had taken images of the same spot on Venus, taken at different times during the mission, and laid them side by side to see whether anything had moved. Robert Herrick, a planetary scientist at the University of Alaska Fairbanks, decided to try. This wasn't a grant-funded initiative with a dedicated team. It was, by several accounts, one researcher with a lot of archived image files and a lot of patience. Herrick spent months doing the comparison manually, looking at radar images of the same locations on Venus taken months apart, trying to find differences. Most of what he looked at showed nothing. The resolution of Magellan's radar was not especially fine, and distinguishing meaningful change from image artifact required care and experience. But Herrick was looking specifically at volcanic features, places where the planet's interior might plausibly express itself at the surface. And at one particular location, he found something. The location was a volcanic structure called Maat Mons. It's one of the largest volcanoes on Venus, a broad, low shield volcano rising about 8 kilometers above the surrounding plains, named after the ancient Egyptian goddess of truth and justice, a name that turns out to be oddly appropriate for a volcano that would eventually reveal something real. Maat Mons had long been a candidate for active volcanism based on indirect clues: elevated temperatures in its vicinity, atmospheric chemistry that seemed slightly unusual near its flanks, but candidate is not confirmed. Indirect is not direct. For decades, nobody had caught it doing anything. Herrick's comparison focused on a volcanic vent associated with Maat Mons, a roughly circular opening in the volcanic structure, the kind of feature you'd expect to find on an active volcanic system. He found images of this vent taken in February of 1991, and images of the same vent taken in October of 1991, 8 months later. When he placed them next to each other, the difference was not subtle. Scott Hensley, a radar scientist at NASA's Jet Propulsion Laboratory in Pasadena, joined the analysis. Together they worked through the technical challenges, the differences in radar viewing angle, the potential for lighting artifacts, the many ways an apparent change in a radar image might not reflect a real change in the surface. They were rigorous about it because they had to be. A claim like this one needs to survive skepticism. It survived. The vent had changed shape. In February of 1991, it appeared roughly circular, covering an area of about 2.2 square kilometers. A vent maybe 1.5 kilometers across, which sounds small but is a substantial opening in a volcanic structure. By October of 1991, 8 months later, that same vent had grown. Its area had roughly doubled, expanding to more than 4 square kilometers. More than that, its shape had changed from that near circle to something more irregular, a kidney shape, elongated and asymmetric. And on the flanks of the vent, in the later image, there appeared to be new material. A lava flow. Fresh volcanic material that had not been there before. Herrick and Hensley published their findings in the journal Science in 2023. What they had found, they argued, was a volcanic vent that had been caught in the act of erupting. Not erupting now, this data was from 1991, a third of a century in the past. But erupting then, during the Magellan mission itself, in real time, while the spacecraft was overhead. The eruption had been happening and the data had been collected, and then it had sat in an archive, unexamined for that specific purpose, for 30 years, waiting for someone to look. Take a moment with that image, a volcano on another world, erupting while a spacecraft silently mapped it from above, capturing the change in radar pulses, storing those pulses as data, transmitting that data back to Earth, where it was archived and processed and catalogued and stored, and then sitting there in a database for 3 decades until a scientist in Alaska with enough patience to go through the images one by one found it. It is one of those scientific discoveries that says as much about archives and attention as it does about volcanoes. The result of the Herrick and Hensley study was, not to be precise, proof that Venus is erupting right now at this moment. What it showed was that Venus was erupting in 1991, but that's important in ways that go beyond the specific date. Because the question with Venus has never really been whether it erupts on geological timescales. The surface age statistics alone suggested as much. The question was whether it erupts on timescales that we might actually observe, years, decades, centuries. And now the answer appears to be yes. A vent changed measurably in 8 months. 8 months is not a geological epoch. 8 months is a very human span of time. This changes the picture of Venus considerably. Before this result, the case for current volcanic activity on Venus rested on indirect evidence, the kind of evidence that points in a direction without quite landing. There were anomalies in the atmosphere's sulfur dioxide content that some researchers argued were best explained by volcanic outgassing. There were regions of elevated surface temperature that seemed harder to explain by passive heat retention alone. There were areas of the planet that, when looked at closely, seemed to have surface properties, emissivity, texture, that might indicate relatively fresh lava. All of this was suggestive. None of it was a smoking gun. The changing vent on Maat Mons is the closest thing to a smoking gun that exists. A physical surface feature caught on radar, documented as changing in shape and size with what appears to be new lava on its flanks. It is as direct as the data allows, and it was hiding in a 30-year-old archive. There is something almost poetic about the timing. The Magellan spacecraft was launched when some of the scientists now analyzing its data were children or not yet born. The mission ended before the internet, as most people now use it, existed, and yet the data it collected was precise enough, careful enough, complete enough that a researcher in 2022 or 2023 could sit down with those images and extract from them a discovery that reshapes the basic understanding of whether Venus is geologically alive. The answer, it turns out, is yes. And once that door opened, others followed through it. In 2024, Herrick and colleagues extended the analysis. Additional comparisons of Magellan images looking at other volcanic regions turned up more evidence of surface change. The regions near Mons, another large shield volcano on Venus, this one named after a Norse goddess associated with earth and grain, showed features consistent with lava flows that had changed in the Magellan image set. The Niobe Planitia region, a broad volcanic plain in the northern hemisphere of Venus, yielded similar results. The 2023 discovery was not an isolated anomaly. It was the first confirmed instance of something that appears to have been happening across the planet, which begins to make sense when you consider the numbers. Over 85,000. That is the count of volcanic features catalogued across Venus's surface in a comprehensive global mapping study published in 2023 by Hahn and Byrne in the Journal of Geophysical Research, Planets. Over 85,000 volcanic structures, and note that word, structures, because it includes features at a range of scales, from tiny cinder cones a few kilometers across to the massive shield volcanoes like Maat Mons and Mons, rising 8 or 9 kilometers above the plains. No other planet in the solar system has been catalogued with this many volcanic features, not Mars, not Mercury, not the Moon. Venus, under its opaque and acid clouds, is the most volcanically featured world we know of. Now, having 85,000 volcanic structures doesn't automatically mean they're all active right now. The Moon has extensive volcanic terrain and hasn't erupted for billions of years. Mars has Mons, the largest volcano in the solar system, and the geological evidence suggests it hasn't seen significant eruptions for perhaps tens of millions of years. Recent in cosmic terms, but well outside human timescales. Having the features doesn't prove current activity, but there's a second piece of evidence that points in the same direction, and it comes from counting craters. When a planetary surface is geologically inactive, when nothing is happening to it, it accumulates craters over time. Meteorites strike, craters form, the craters pile up, and the density of craters becomes a clock. The older the surface, the more craters. The younger the surface, the fewer. Astronomers use this relationship, calibrated against surfaces we know the ages of, primarily the Moon, where we have rocks with datable isotopes, to estimate the ages of surfaces elsewhere. On Venus, the crater count is peculiar. The craters are there, while a few hundred of them, which is not many, and they're distributed more or less randomly across the surface. If you run the statistical analysis, the average implied surface age works out to somewhere between roughly 300 and 700 million years. That is far, far younger than the Moon's ancient highlands, which preserve craters going back more than 3 billion years. It's younger than the heavily cratered terrain of Mars. 300 to 700 million years is geologically recent. It puts the Venusian surface as having been renewed sometime in the interval when complex animal life was first evolving in Earth's oceans. But here's the thing that makes Venus's crater distribution even stranger. On most planetary bodies, older regions accumulate more craters than younger regions. You get a patchwork, some areas heavily cratered and ancient, others smoother and younger. That patchwork tells the story of a dynamic world with different regions resurfaced at different times by different processes. Mars shows this, the Moon shows this. Venus doesn't show this. Its craters are distributed remarkably uniformly across the surface. There isn't a heavily cratered old region and a sparsely cratered young region. The whole planet seems to be roughly the same age. The interpretation that many planetary scientists have settled on, cautiously, because Venus is still poorly understood, is that Venus underwent some kind of global resurfacing event. Something happened, possibly a catastrophic outpouring of volcanic material on a planetary scale, that buried or obliterated whatever craters existed before it and left a fresh surface across essentially the entire planet. After that event, the volcanism settled into something lower level, the crater count began accumulating again, and that's the surface we see with Magellan's radar today. The surface is 300 to 700 million years old on average, because it all dates from roughly the same resurfacing event. Whether that catastrophic resurfacing is the entire story, whether Venus cycles between periods of low-level volcanism punctuated by episodes of global volcanic outpouring, or whether the current period is one of dying down activity, or whether it is genuinely still vigorous, that is one of the core unknowns. But the Magellan-era changing vent, the 2024 follow-up detections near Mons and Niobe Planitia, the 85,000 volcanic features, and the statistically young surface all point in the same direction. Venus is not a dead world. It is a world whose interior is still warm enough, still active enough, still restless enough to push material toward the surface on time scales that are not just geological abstractions, but real, observable, detectable timescales. A timescale that Magellan happened to sample for 4 years in the early 1990s without anyone realizing what it had caught. And there is something quietly significant about the fact that this discovery came not from a new mission, not from a purpose-built instrument, not from a dedicated modern study with real-time observation, but from old data. Magellan was designed to map Venus's terrain. It was not designed to monitor volcanic eruptions in progress. It was not designed to detect surface change. The radar it carried was good enough, just barely good enough, to catch a vent doubling in size over 8 months, and that capability sat unused for 3 decades until the right person asked the right question. What else is hiding in the archive? That's not a rhetorical flourish, it's a real question being asked by real researchers. The Magellan dataset, for all its limitations, covers nearly the entire planet, with radar images taken at multiple times during the mission. The analysis has only just begun in earnest. The vent at Maat Mons was found because Herrick was specifically and patiently looking for change. The regions near Mons and Niobe Planitia were found as the methodology was extended. The planet has not been fully searched for this kind of signature. There are almost certainly more instances waiting, more features that changed, more evidence of activity, more moments when Venus was doing something and Magellan's radar was watching without knowing what it was witnessing. 30 years of archive. 98% of the planet's surface. A methodology that now exists and has been validated. The next several years of archival analysis alone, without any new spacecraft at all, could substantially change what we know about when and where Venus is active. But the 2030s will bring something better than old archives. The 2030s will bring new eyes. Before we get there, and we will, there's one more facet of Venus's volcanic character worth lingering on because it connects the geological story back to the atmospheric story in a way that makes the whole picture cohere. Recall the atmosphere, the thick CO2, the sulfuric acid clouds, the super-rotating upper layers, the crushing surface pressure. Think about where that atmosphere came from. An atmosphere as dense as Venus's, 92 times the surface pressure of Earth's, did not arrive from outside. It is not leftover primordial gas from the solar system's formation. It came from inside the planet. Over billions of years, volcanic eruptions outgassed carbon dioxide and sulfur compounds and other volatiles from Venus's interior. The atmosphere of Venus is, in a very real sense, the exhalation of Venus's interior, which means that if Venus is still volcanically active, and the evidence now suggests it is, then Venus's atmosphere is not a static artifact, not a fixed endpoint, not a final state of a climate catastrophe that concluded long ago. It is being actively maintained and modified by ongoing geological activity. The volcanism that built the atmosphere may still be adding to it. Sulfur dioxide that appears to fluctuate in the atmosphere may be, at least in part, from recent or ongoing eruptions. The connection between what is happening in the rock and what is happening in the air is not historical. It may be current. A 2020 study by Truong and Lu Nin, published in the Proceedings of the National Academy of Sciences, explored exactly this. Their analysis suggested that ongoing volcanic outgassing could help explain some of the chemical peculiarities in Venus's atmosphere. That the planet's volcanism isn't just geological texture on a dead backdrop, but an active ingredient in the atmospheric system. The atmosphere and the interior are still talking to each other. The climate catastrophe and the geological vitality are not separate stories from separate eras. They are happening on the same world at the same time, woven together. This is what the dead furnace frame misses. The furnace isn't dead, it's being stoked. And the stoking is connected in complex ways we don't yet fully understand to the climate. The carbon dioxide that drives the runaway greenhouse was released by volcanism. The sulfuric acid clouds contain sulfur compounds that also come, ultimately, from volcanic outgassing. The atmosphere that crushes and roasts and burns is the cumulative output of a geologically active interior that has been exhaling for billions of years and may still be exhaling now. Venus is not a cautionary tale of what happens when a world goes wrong and then stops. It is a cautionary tale of what happens when a world goes wrong and keeps going, that reframing matters because if Venus's volcanism is ongoing, and if that volcanism is contributing to the atmospheric chemistry, then Venus is not in a final state. It is in an ongoing state, a state of continued geological expression, pumping material into an atmosphere that is already at an extreme. The end point the title promised, the lethal furnace world, is not a fixed destination already arrived at. It is a trajectory still in motion, which makes the science of Venus not just a retrospective autopsy. It makes it the study of a living system, strange and hostile and extreme, but alive in the geological sense of that word, still doing things, still changing, slowly, at timescales that dwarf a human life but that can be glimpsed in 8-month radar comparisons from 1991, in atmospheric sulfur dioxide fluctuations, in the thermal anomalies, and the 85,000 volcanic features scattered across a planet that has never let anyone stand on its surface for more than 2 hours. No lander has survived longer than that. Venera 13, the most successful surface lander humanity has ever sent to Venus, touched down in March of 1982, returned the first color photographs of the Venusian surface, a rocky, orange-lit plain stretching out under a crushing, hot, rust-colored sky, and stopped transmitting after about 127 minutes. Not because anything went wrong with the landing or the instruments, simply because the environment destroyed the spacecraft. The heat and pressure that make Venus what it is are not obstacles to be engineered around with a bit more shielding. They are genuinely extreme in ways that put hard limits on what any object made of current materials can survive. 127 minutes, then silence. And yet those images, grainy, warm-toned, alien, are some of the most remarkable photographs ever taken. A surface nobody has seen with human eyes. A sky full of thick, orange-yellow cloud, lit by diffuse light with no visible sun. Rocks weathered and split, some flat like paving stones, stretching away until the haze swallows them. No water, no ice, no movement except the slow creep of winds too thick to be casual breezes. The densest, most hostile surface environment any human-built object has ever survived. And the pictures it sent back are the only direct, visual, surface-level evidence we have of what that world actually looks like. Venera 13 was the 12th spacecraft in the Soviet Venera program, a sequence of missions that spanned from the 1960s to the 80s, and that represents, even now, the most sustained exploration of any planetary surface that has never been revisited. Venera 7, launched in 1970, was the first spacecraft ever to successfully land on another planet and return data. It survived for 23 minutes on the surface, transmitting temperature and pressure readings that confirmed what calculations had suggested. Venus's surface is 474 degrees Celsius, and the pressure is 9 times what anyone had hoped. The data was so extreme that scientists initially thought the instruments had malfunctioned. They hadn't. The subsequent Veneras refined the picture, each mission building on the last, each one a small engineering miracle of heat shielding and cooling systems and compressed timelines, because every design decision was constrained by one brutal reality. The spacecraft had to do everything it needed to do before the heat and pressure killed it. There was no margin for slow data collection, no margin for waiting for good conditions. The moment a Venera lander touched the Venusian surface, the clock started, and the clock was merciless. The Soviet engineers knew this. They built accordingly. And in Venera 13, they built something that lasted long enough to turn a camera and photograph the ground it was standing on in color and send those photographs across 104 million kilometers of space to Earth. Those photographs, those 127 minutes, are still the sum total of humanity's direct surface experience of Venus, No human mission has followed. No robotic successor has made it down through the atmosphere and onto the rocks and survived. The surface of Venus remains, as of this night you're listening, essentially unvisited since 1982. That's over 40 years of silence from the surface of the nearest planet. And now, quietly, that is about to change. But before we get to what's coming, before we talk about the missions being assembled right now for the 2030s, there's something we need to sit with first, something that changes the framing of everything else. Because for most of the decades between Venera 13 and today, Venus was described in a particular way. The word that kept appearing in papers and in popular accounts and in the kind of shorthand scientists use when they're not being careful was dead. A dead world, a furnace, a place where geology had finished its work, where the internal fires had banked, where what you saw on the surface was what you were going to see for the foreseeable future, a record of catastrophe, not an ongoing one. And that framing was understandable. It wasn't careless. It came from the evidence available. It was also, it turns out, probably wrong. Here is what Robert Herrick did. Herrick is a planetary scientist at the University of Alaska Fairbanks. He had spent years working with the data returned by NASA's Magellan spacecraft. The mission that between 1990 and 1994 mapped 98% of Venus's surface by radar. Radar because the clouds let nothing else through. The cameras and spectrometers that work so well elsewhere in the solar system are simply useless at Venus. The planet keeps its surface hidden. Magellan used radio waves instead, bouncing pulses off the ground and building up a picture from the echoes, and what it built was the most detailed global map of Venus ever made. And then the mission ended, and the spacecraft was deliberately sent into the atmosphere in October 1994, and the data went into an archive, and the scientific community moved on. For about 30 years, those images sat there. Herrick went back to them. What he was looking for, specifically, were signs of change. The idea was straightforward in principle. If Venus is geologically active, then the surface should look different at different times. Magellan didn't image the whole planet at once. It built its map, strip by strip, over multiple orbital passes, which meant that some features were captured more than once, at different points during the mission. If you could find two images of the same feature taken months apart and compare them carefully enough, you might see whether anything had moved. The problem was that carefully enough is doing a lot of work in that sentence. The resolution of the Magellan radar images is good, but it is not perfect. Surface features can look subtly different between passes simply because of geometry. The angle of the radar beam, the orientation of the spacecraft. Telling real change from instrumental artifact requires patience. It requires, honestly, a willingness to spend a long time staring at images that mostly look the same. Herrick was willing. He and his colleague, Scott Hensley, from NASA's Jet Propulsion Laboratory, spent months on it, manually comparing image pairs, looking for anything that didn't match. They found it at Maat Mons. Maat Mons is one of Venus's largest shield volcanoes, broad, low, built by repeated flows of lava over long timescales, similar in shape to the volcanoes of Hawaii. On Earth, shield volcanoes can be quite active. On Venus, Maat Mons had long been flagged as a candidate for recent activity, mostly because the terrain around it appeared young in crater counts and radar backscatter. But appeared young is geological shorthand for something that could mean 50 million years ago. It was suggestive, not conclusive. Then Herrick and Hensley compared two radar images of a volcanic vent on Maat Mons's northern flank. One image was taken in February 1991. The other was taken 8 months later, in October 1991. The vent had changed. In February, it was roughly circular, with an area of about 2.2 square kilometers. By October, it had grown, more than doubled, to over 4 square kilometers, and the shape had shifted from something close to a circle into an irregular, kidney-shaped outline. On the flanks below it, there appeared to be what Herrick and Hensley interpreted as a new lava flow, material that had not been there in February. They published this in the journal Science in 2023. Take a moment with what that means. A volcano on Venus was caught in the act of erupting, not inferred, not modelled, not suggested by atmospheric chemistry that could mean several things. The physical surface of the planet, a vent on its flank, visibly changed between two observations 8 months apart. The dead furnace framing, at the comfortable shorthand of decades, broke on contact with 30-year-old data that nobody had looked at closely enough. The data was never missing, the answer was in the archive the entire time. And that is a particular kind of scientific moment, the kind that tends to make people go a little quiet when they hear about it. The discovery wasn't made by a new spacecraft with better instruments. It wasn't made by a breakthrough in imaging technology. It was made by a researcher sitting with archived files and a willingness to look again, slowly and carefully, at something that had been catalogued and set aside. Herrick reportedly spent months on that comparison, months of looking at image pairs, most of which showed nothing, before finding the one pair that showed something extraordinary. That is worth remembering because the result is often described in headlines as a sudden revelation. It wasn't. It was slow, deliberate, painstaking work, the kind that rarely gets dramatized but is, in practice, how a large fraction of science actually gets done. The 2023 paper mattered immediately because it shifted the question from might Venus be active to Venus is active. Now how active and how recently and where else? Those are better questions. They are more tractable questions, and they pointed directly back at the Magellan archive. If one vent had changed on Maat Mons, what else might be in there? Follow-up work began almost immediately. By 2024, Herrick and colleagues, along with separate analysis teams, had identified additional surface changes in the Magellan data consistent with lava flows, not just at Maat Mons but in other regions, including areas near another large volcanic edifice called Sif Mons and a highland region called Niobe Planitia. The pattern was becoming harder to dismiss. Venus was not a dead furnace. Venus was erupting, possibly repeatedly across multiple locations, during the years that Magellan was watching. We just hadn't noticed. The spacecraft had done its job faithfully, collected its data, sent it home, and then the data waited in storage while a generation of scientists worked with it at the global scale, building maps, cataloguing features, counting craters, without quite getting to the frame-by-frame comparison that would reveal the motion underneath. None of this is entirely surprising if you step back and look at the larger picture of what Venus is. Over 85,000 volcanic features have been catalogued on Venus's surface, more than on any other planet in the solar system. That count comes from a 2023 global survey by Hahn and Byrne, published in the Journal of Geophysical Research, Planets, and the sheer number of it is difficult to sit with comfortably. 85,000. Small shield volcanoes mostly clustered in volcanic plains and spreading across the highlands, but also large edifices like Maat Mons and Sif Mons, and strange features that have no real Earth analogue, structures called coronae, circular or oval collapsed formations that may mark where hot plumes from the mantle pushed up against the crust from below. And then there is the question of the surface age. Planetary scientists estimate the average age of Venus's surface by counting impact craters. The logic is simple: older surfaces accumulate more craters over time, so a heavily cratered surface is an old one, and a lightly cratered surface is a young one. Venus has relatively few craters, far fewer than the Moon, far fewer than Mars, and they are distributed fairly uniformly across the planet. The crater count suggests that the average surface age is somewhere between 300 million and 700 million years, which in geological terms is recent. Earth is 4.5 billion years old. Venus is approximately the same age. It formed from the same solar nebula at roughly the same time, but its surface looks only a few 100 million years old. That gap between the planet's age and its surface age needs an explanation, and the most widely accepted one is that something, possibly a series of massive volcanic events, possibly one catastrophic global resurfacing episode, essentially paved over whatever came before. The old surface is gone, a new one replaced it, and if the 2023 and 2024 findings are any guide, the process that makes new surfaces on Venus has not stopped. And then there is the clockwork. Because before we get to what humans did to reach Venus, and before we talk about what they are planning to send there next, it is worth pausing for a moment on the way Venus actually moves through space and spins on its axis. Because if you think Earth has some unusual properties, Venus is doing something so strange that it almost seems deliberate, as if someone took a planet and decided to run it backwards and slow it down just to see what would happen. Let us start with the most disorienting fact. One Venusian day, with the time it takes Venus to complete one full rotation on its own axis, is 243 Earth days long. That is longer than a Venusian year. A year on Venus, the time it takes to complete one full orbit around the Sun, is only 225 Earth days. So Venus is rotating so slowly, so incredibly, absurdly slowly, that it makes a complete trip around the Sun before it finishes a single turn on its axis. The year ends before the day does. If you were born on Venus and you celebrated your birthday each time the planet completed an orbit, you would never once have experienced a full day between birthdays. And it gets stranger. Venus rotates backwards. On Earth, and on most of the planets in the solar system, the direction of rotation and the direction of revolution, the direction of spinning and the direction of orbiting, are the same. Earth spins counterclockwise when viewed from above the North Pole. It orbits counterclockwise as well. That alignment makes sense. Everything in the early solar system formed from the same rotating cloud of gas and dust, so the spin tends to go the same way. Venus spins clockwise, or more precisely, Venus is tilted almost completely upside down. Its axial tilt is about 177 degrees, which is essentially a full flip. Whether you call it spinning backwards or spinning upside down is partly a matter of convention, but the practical result is the same. If you were somehow standing on the surface of Venus, which, as we have already discussed, would not be a long or pleasant visit, and if the cloud deck were somehow transparent enough to see the sky, the sun would rise in the west and set in the east, not because of any trick of the clouds, but because the planet itself is moving the wrong way. Nobody is entirely sure why. One leading idea is that Venus suffered an enormous collision very early in its history, the kind of planetary billiard shot that would have knocked its rotation into reverse and tipped it over. Another possibility is that the combination of gravitational tides from the Sun and the atmospheric tides driven by the thick atmosphere gradually slowed Venus's original spin and then flipped it over billions of years, like a top slowly losing its precession and tipping the other way. The models suggest both are possible. The dossier is not settled, and without knowing what the original spin was and without knowing what Venus looked like in its first billion years, it is genuinely hard to say which story is right. Da Vinci and Veritas and Envision may eventually help untangle it, but for now the clockwork is what it is: a day longer than a year, a sun that rises in the wrong direction, a spin so slow and so backward that it barely seems like spinning at all. And yet, and here is the next strange thing, the atmosphere is not slow at all. While the surface of Venus creeps through one rotation in 243 Earth days, the clouds above it are racing. The upper atmosphere of Venus super-rotates. That is the actual technical term, super-rotation. The entire atmospheric layer, those thick sulfuric acid clouds at roughly 48 to 70 kilometers altitude, is circling the planet in about 4 Earth days. At the cloud tops, wind speeds reach approximately 360 kilometers per hour, faster than the strongest hurricanes on Earth, sustained and planet-wide, spinning in the same direction all the way around. So you have a situation where the planet is barely turning and the air above it is screaming around in circles every 4 days. The atmosphere spins roughly 60 times faster than the planet beneath it. Atmospheric scientists have understood since the Pioneer Venus mission that this super-rotation is real and global, but the full dynamical explanation for how it is maintained, how the planet keeps energizing those upper winds despite barely rotating itself, is still not completely worked out. It is one of those quietly fascinating problems that hides behind the more dramatic headlines about volcanoes and acid clouds. Down at the surface, by contrast, the winds are almost calm, only a few kilometers per hour. A gentle breeze, nothing more. But here is the catch. The atmosphere at the surface of Venus is not gentle even when the wind is slow. The carbon dioxide is so dense down there, 92 times the pressure of Earth's sea level, remember, like standing 900 meters underwater, that even a slow-moving CO2 atmosphere carries enormous momentum. A light surface breeze on Venus would not feel like the light breeze you feel on your porch on a warm evening. It would feel like being pushed by a slow current underwater. The fluid itself is thick enough that even modest motion translates into significant physical force. The atmosphere down there is almost more liquid than gas in the way it behaves. The Soviet engineers who designed the Venera landers understood this, and they built accordingly. And it is worth spending a little time with the Venera program because it represents one of the most remarkable chapters in planetary exploration. A story of ingenuity and courage, and ultimately of a world that simply refused to be lived in. The Soviet Union's Venera program ran for decades, beginning in the early 1960s and continuing through the mid-1980s. It was the most sustained planetary program in history up to that point. Early Venera probes were destroyed almost immediately, crushed by pressure or burned by heat before they could return useful data, because nobody on Earth yet knew how extreme the surface conditions truly were. Each failed mission taught the engineers something. They built stronger, heavier, more insulated landers. They added titanium shells. They designed the spacecraft to survive long enough to take measurements and then, inevitably, die. Venera 7 landed on Venus on the 15th of December, 1970. It was the first spacecraft in history to land on another planet and successfully return data from the surface. It transmitted for 23 minutes before succumbing to the heat. The data it sent back confirmed surface temperatures near 470 degrees Celsius and pressures near 90 atmospheres. The numbers that came back were so extreme that scientists initially questioned whether the probe had actually landed or was still in the atmosphere. It had landed. The surface was just that hostile. 12 years later, Venera 13 landed on the 1st of March, 1982, and it did something extraordinary. It survived on the surface for 127 minutes, the longest any craft has ever survived on Venus. And it returned the first color images of the Venusian surface. Think about what those images showed. An orange-lit rocky plain stretching away under a sky that glowed, with an eerie amber light filtered through the thick cloud deck high above. Flat, dark rocks with sharp edges, suggesting they had not been eroded by water or wind for very long. A bleak, alien landscape that looked like the bottom of a furnace, which, in a very real sense, it was. Orange and brown and ochre, lit by a diffuse reddish light with no shadows, because the cloud deck scatters light in every direction. It was not the dramatic science fiction landscape of craters and dust storms. It was quieter than that. more oppressive. The rocks just sat there on a hot, still, dying plain. Then the heat and pressure claimed the spacecraft, as they always do. No lander has ever survived more than about 2 hours on Venus's surface. That is the hard ceiling. Not because of design failure, but because the environment eventually wins. The materials give out, the seals fail, the electronics fry, the pressure works through any gap it can find. There is a reason Venus has had fewer successful surface missions than the Moon, fewer than Mars, fewer even than Jupiter's atmosphere, and Venus is our nearest planetary neighbor. The surface is simply not survivable for very long with any technology we have built so far. And yet, that is not the end of the story of Venus and the possibility of something more than inert rock and heat. Because as you rise up through Venus's atmosphere, as you climb away from that crushing, roasting surface and ascend through the lower atmosphere and up toward the cloud deck, something unusual happens. The conditions change. The temperature drops. The pressure drops. And at a certain altitude, they drop to something surprisingly familiar. At roughly 50 kilometers above the surface of Venus, roughly 50 to 55 kilometers up within the lower part of that great cloud deck, the temperature sits at somewhere between about 30 and 70 degrees Celsius. And the atmospheric pressure at that altitude is approximately 1 bar. 1 bar, Earth's sea-level atmospheric pressure. That cloud layer, 50 kilometers above the Venusian surface, is the most Earth-like environment anywhere in the solar system outside of Earth itself. Temperature, pressure, both within ranges that human bodies are built for, roughly. It is, by those two measures alone, the most hospitable extraterrestrial environment we know of. Of course, there is a problem. The clouds at that altitude are made of concentrated sulfuric acid. The droplets in the cloud layer are not water. They are H2SO4, sulfuric acid, at concentrations that would destroy most biological molecules on contact. If you were floating there in a balloon, as some researchers have seriously proposed doing, you would be in a survivable pressure and temperature, but the chemistry around you would be deeply hostile to life as we know it. And yet, life on Earth is not shy about sulfuric acid. Certain extremophiles, organisms that live in the most hostile environments on our planet, thrive near volcanic vents, in acid pools, in conditions that would kill most living things instantly. The question of whether any chemistry in Venus's cloud layer could sustain anything remotely like biology is not a closed question. It is genuinely open. And it became considerably more publicly open in 2020. In September of that year, a team led by Jane Greaves announced the detection of phosphine in Venus's atmosphere. Phosphine is a molecule, pH3, 1 phosphorus atom, bonded to 3 hydrogen atoms. On Earth, phosphine is produced in certain industrial processes, and it is also produced by some microbes in low-oxygen environments. The point is that on a rocky world like Venus with its oxidizing sulfuric atmosphere, there is no obvious non-biological chemistry that produces phosphine in the amounts the team reported detecting. The announcement made headlines around the world. The suggestion, stated carefully and with appropriate caveats by the scientists themselves, was that either there was some unknown chemistry producing phosphine in Venus's clouds, or the possibility that generated the headlines, there were microbial scale organisms up there doing it. The scientific response was immediate and vigorous. Subsequent analyses of the same data by other teams found weaker signals than Greaves's team had reported, or questioned the data processing methods that had been used. Some analyses found no clear phosphine signal at all. Others found a signal but at much lower abundance than initially claimed. The source telescope's data was re-examined. Arguments went back and forth. As of the time this script was written, the phosphine detection is contested, the signal is uncertain, and no consensus has formed that Venus's clouds contain phosphine in any definitive amount. There is no confirmed detection of life on Venus. The question is not resolved. the story is not over. But here is why it is worth telling carefully without overselling it. The very fact that scientists took the phosphine question seriously, the fact that it sparked years of debate and reanalysis and instrument proposals, tells you something real about Venus's cloud layer. It tells you that scientists who study the chemistry of extreme environments genuinely consider the temperate Venusian clouds a plausible place to investigate for the possibility of life, not because we have found any, but because we have not definitively ruled it out, and because the conditions are strange and interesting enough that the question deserves real instruments and real data rather than a dismissal. And there is another thread worth pulling here. In 2020, a separate study by Truong and Lunin, looking at the deuterium to hydrogen ratio and atmospheric chemistry on Venus, proposed that ongoing volcanic outgassing might be actively contributing water and other volatiles to Venus's atmosphere. In other words, Venus's atmosphere may not be a static remnant of some ancient catastrophe. It may be a living system actively maintained and altered by ongoing volcanism even today. Think about what that would mean. It would mean that Maat Mons and the other active volcanic features on Venus are not just geological curiosities. They are participants in the atmospheric chemistry of the planet in real time. The lava that erupted from that vent between February and October of 1991, the eruption Robert Herrick and Scott Hensley found hiding in the Magellan archives, may have contributed gases to an atmosphere that still shapes temperature, still traps heat, still drives the clouds around the planet at 360 kilometers per hour. The geology and the climate are not separate stories. They are the same story, still being written. This is what it means for Venus to be a living world, not alive with organisms necessarily. That question remains open and honest, but alive in the sense that matters geologically, climatically, and scientifically. Venus is not a fossil. It is not a museum exhibit of a dead planet. It is an active system, active volcanism, active atmospheric chemistry, active climate processes, all running on a world that looks from the outside like a finished disaster. And the most important thing we know about it, the thing that makes Venus relevant not just as a curiosity but as a cautionary mirror, is that it started from the same place we did. Same size roughly, same mass, same gravity, same distance from the same star, give or take, same original inventory of carbon dioxide which on Earth got locked into limestone and dissolved into oceans by the carbon silicate cycle, and on Venus stayed in the air. Same origin story. One of them became a world with clear skies and liquid water and life and seasons and snowfall and thunderstorms and blue oceans and green land. The other became a 465-degree acid furnace with a carbon dioxide atmosphere 92 times as thick as ours and no magnetic field to protect it, and a day longer than its year, and a surface that destroys any machine we land on within 2 hours. The same starting materials, completely different outcomes. That is the question that is driving 3 separate space agencies to Venus in the 2030s, and it is worth talking about each of those missions because they are not redundant. They are asking genuinely different questions, and they are going to need each other's answers. The first is Da Vinci. The full name is the Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging. NASA selected it in 2021 and it is targeting launch in the early 2030s. Da Vinci is primarily an atmospheric probe mission. The plan is to release a descent probe, a sphere protected against the temperature and pressure, that will fall through Venus's atmosphere over about an hour, sampling the chemistry on the way down. It will measure noble gases, the inert elements like argon and neon and xenon that do not react with much, and therefore carry pristine information about where the atmosphere originally came from and how it has evolved. It will also measure isotope ratios, including the deuterium to hydrogen ratio that tells us about ancient water. And as it falls through the lowest part of the atmosphere, it will take the first high-resolution images of Venus's tessera terrain, those ancient, heavily deformed highland plateaus that may be the only remnants of whatever surface existed before the global resurfacing event, captured from below the clouds with a camera that can see what no spacecraft has seen before. The central scientific question for Da Vinci is, did Venus ever have an ocean? If the noble gas abundances and the isotope chemistry in the deep atmosphere match what you would expect from a world that once had liquid water on its surface, if the chemical fingerprints of that ancient ocean are still encoded in the deep air, then Da Vinci may be able to detect them. It will not be a simple readout, and the interpretation will take time and debate, but the data Da Vinci brings back will be the most direct evidence we have ever gathered on whether Venus was once a livable world. The second mission is Veritas, Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy. The acronym was clearly worked very hard. Veritas is also a NASA mission selected in 2021, and it is an orbiter designed to do for Venus what we should have done 30 years ago after Magellan: map the surface at dramatically higher resolution, detect ongoing geologic deformation and volcanic activity in near real time, and characterize the surface composition through emission spectroscopy. Veritas would be, in essence, a next-generation Magellan, a radar mapper with vastly better instruments than the one that produced the images Robert Herrick spent months poring over by eye. If Veritas had been in orbit when Maat Mons erupted in 1991, we would not have had to wait 30 years to discover it. We would have seen it as it happened. Veritas's schedule has been affected by NASA budget pressures, but it remains planned for the 2030s, and its scientific case has only gotten stronger as the evidence for ongoing volcanism has accumulated. The third mission is Envision. Envision is the European Space Agency's contribution to the new wave of Venus exploration, and it was selected in 2021 alongside the NASA missions. It is an orbiter planned for launch around 2031, and its ambition is perhaps the broadest: to study Venus from its inner core to its upper atmosphere, looking at the full system together. It will carry radar for surface mapping, instruments to detect volcanic emissions and atmospheric chemistry, and sensors to look at how the solar wind interacts with the upper atmosphere, the stripping process that may have helped Venus lose its water billions of years ago. Envision is designed to see Venus whole as a system, not just to study one part of it. 3 missions, 3 different agencies, 3 different questions asked simultaneously. And that convergence, that sudden rush of attention toward a planet that went largely unvisited for the better part of 30 years, is itself a signal. It tells you that the scientific community has concluded that Venus is not a solved problem. It is not a planet we understand. It is a planet we barely know, wrapped in clouds that have hidden its surface for most of human history, its geology caught in the middle of processes we cannot yet name, its past holding answers to questions about Earth's future that we cannot afford to leave unasked. And here is the thing that tends to sit quietly underneath all of these conversations about Venus: the thought that surfaces when you step back from the individual facts. The vent that changed shape, the DH ratio, the phosphine debate, the carbon-silicate cycle. And look at the picture whole. Earth is Venus. Not literally, not now, but Earth and Venus are the same experiment run with slightly different initial conditions, and one of those experiments went wrong. On Venus, the carbon dioxide stayed in the air. The oceans evaporated. The water vapor amplified the warming in a loop that ran away from anything that could check it. The hydrogen escaped to space. The carbon that might have been locked into rock and ocean sediment under a water cycle never got a chance to be buried because there was no water left to bury it. And now the entire CO2 inventory of a planet sits in the atmosphere, trapping heat, cooking the surface, maintaining a system that is in some sense perfectly stable. Not because it is hospitable, but because all the mechanisms that might have corrected it are gone. On Earth, the carbon is mostly in the rock, in the limestone, in the coral reefs and the ocean sediments and the carbonate formations that line the walls of cliffs all over the planet. The carbon-silicate cycle, the long, slow geological cycle in which carbon dioxide weathers silicate rocks and gets washed into the ocean and eventually buried in seafloor sediments and then returned to the atmosphere by volcanic outgassing over millions of years. That cycle keeps Earth's atmospheric CO2 within ranges that liquid water can exist in. It is not automatic. It is not permanent. It requires liquid water and weathering to run. And it has kept Earth's temperature remarkably stable over geological time, not because the climate never changed, but because the cycle is a thermostat, correcting over long time scales. Venus no longer has that thermostat. It broke, or it never fully got started, or the brightening sun pushed the system past a threshold that liquid water on the surface could no longer survive. And once the water was gone, the thermostat was gone. The CO2 had nowhere to go. It stayed in the air forever, trapping everything. If you took all of the CO2 currently locked in Earth's carbonate rocks and sediments, all of it, accumulated over billions of years of the carbon-silicate cycle running quietly in the background, and you released it into Earth's atmosphere at once, you would have an atmosphere very much like Venus's. The carbon is there. It is just in a different place. The question of where your planet keeps its carbon is not a trivial question. It turns out to be one of the most consequential questions a planet can answer. Venus answered it wrong, or it answered it right for a long time, and then something changed and the answer flipped, and now there is no way back. That is the cautionary mirror. Not a vague warning about distant futures, but a specific, concrete, chemically verified demonstration that a planet nearly identical to Earth can end up with all of its carbon in the air and all of its water lost to space and a surface temperature high enough to melt lead uniformly everywhere, day and night, pole to equator, forever. That world is our neighbor. It is 8 minutes away at the speed of light. On a clear night, if you know where to look, you can see it with your naked eye. The brightest thing in the sky after the moon, bright enough to cast a faint shadow on the ground below you, bright enough that ancient cultures who watched the sky carefully enough recorded it as two different objects before they understood that the morning star and the evening star were the same planet, catching sunlight from different angles as it orbited ahead of and then behind the sun. They thought it was two things. It was one thing all along, and what it is, we are still in the middle of learning. Right now, somewhere in the archives, in hard drives at NASA's Jet Propulsion Laboratory and at the University of Alaska Fairbanks and at the other institutions that hold copies of the Magellan data, there are more images waiting, more pairs of radar swathes taken months apart in 1990 and 1991 and 1992, images that no one has yet compared the way Robert Herrick compared the ones of Maat Mons, sitting at a screen and scrolling through old data by hand, looking for something that moved. After the 2023 paper, after the 2024 follow-ups near Sif Mons and Niobe Planitia, the question is not whether Venus is volcanically active. The question is how active, and how recently, and where else. Those answers are in the archive, and they are also in the data that Veritas will collect, in the descent chemistry that Da Vinci will measure, in the whole system portrait that Envision will slowly build over years of orbiting. The 2030s are going to be extraordinary for Venus science, not because we will fly there with humans. We will not yet, not for a long time, but because we are sending the best instruments we have ever built to a world we should have been studying more carefully for the last 30 years. We are going back to the twin. We are going to ask it, finally, with real instruments and real patience, what exactly happened to it. Wherever you are right now, as you are listening to this, if you are lying in the dark, if the lamp is still on somewhere in the room, if you are on a train or a bus or a couch at the end of a long day, you are on a planet that got lucky. Or more than lucky, a planet that had liquid water and kept it and built a carbon cycle around it and used that carbon cycle as a thermostat and somehow managed to remain within the narrow band of temperatures where water stays liquid for 4.5 billion years, long enough for something to learn to breathe and build cities and point radio telescopes at the sky and eventually send small titanium machines to die on the surface of its sister world. The air you are breathing right now is not mostly carbon dioxide. It is 78% nitrogen and 21% oxygen and a small fraction of other things. And when you breathe out, you add a little CO2 to it, but then the plants take it back, and the ocean absorbs some, and the limestone that is forming at the bottom of shallow seas somewhere is pulling some out of the cycle and locking it away. That whole quiet system is running right now while you are lying there. You are inside the thermostat. You are part of it. The Earth's carbonate rocks and oceans and weathering cycles are what stand between this planet and 465 degrees, and the fact that they are still running is not something to take for granted. Venus took it for granted, or rather Venus never had the chance not to. The system that might have saved it either broke too soon or was never quite stable enough, and now the evidence is written in the DH ratio of its upper atmosphere, in the ghost of a vanished ocean measured in heavy hydrogen, in the thick acid clouds and the 92-bar surface, and the vent on Maat Mons that changed shape in 8 months, and then sat unnoticed in an archive for 30 years. You are breathing because Earth kept its water. Think about that for a moment gently as you settle a little further into wherever you are. This planet held on to its oceans. It locked its carbon into rock. It ran the carbon silicate cycle for longer than the gap between you and the first single-celled organisms on this planet is even able to comprehend, and it is still running. The volcanoes are still cycling carbon back into the air, and the rain is still weathering it back out of the air, and the seafloor is still burying it, and the system goes around. On Venus, the cycle stopped, or it ran out of water to run it. And the result is the brightest light in your night sky, a 465-degree furnace wrapped in sulfuric acid, rotating backwards so slowly that a day outlasts its year, with a volcanic surface that is geologically only 300 to 700 million years old, with a volcano on its flank that was caught mid-eruption in radar data taken by a spacecraft launched before the internet existed, discovered by a scientist patiently comparing images on a screen decades later. Venus is not a warning from the future. It is a record of a different past. A road not taken made solid and real and visible in the night sky. A twin that went another way for reasons we are still untangling, and ended up somewhere we can see but cannot visit for more than 2 hours before the world itself closes in. The 2030s will tell us more. Da Vinci will fall through that ancient crushing air and taste the chemistry of a world that may once have had oceans, and the numbers it measures will either confirm the ghost of that water or push us toward another explanation. Veritas will map the surface with resolution that makes Magellan look like a rough sketch, and it will find the other changed vents, the other lava flows, the other signs of a world still remaking itself from the inside. Envision will watch the whole system breathe, if breathing is the right word for what Venus does. The slow exhalation of sulfur from volcanic vents, the acid cycling through the clouds, the solar wind picking at the edges of the upper atmosphere and carrying atoms of hydrogen off into space, one by one, the same process that bled Venus dry of its water over billions of years. And somewhere in all of that data, the answer to the central question will begin to take shape. Not suddenly, not with a single headline, but slowly in the way science actually works, with papers and rebuttals and revised models and arguments at conferences and measurements taken again to make sure. The question of why Venus and Earth diverged, whether it was the brightening sun crossing a threshold or a catastrophic volcanic resurfacing that flooded the atmosphere with CO2 before the silicate weathering cycle could respond, or the early loss of the magnetic field that allowed the solar wind to strip the upper atmosphere and accelerate the water loss. That question does not have a clean answer yet. But it will have a better one by the time those 3 spacecraft have done their work. And in the meantime, Venus is there. Circling in its slow backward way, its clouds catching the sunlight and throwing most of it back, bright enough to see from your backyard on a clear night even now, if the clouds above you are not too thick. Back at the very beginning of tonight, I asked where in the world you are watching from. Maybe you are still awake to answer. Maybe you drifted off somewhere in the middle of the Runaway greenhouse, or somewhere in the Venera landers last 2 hours on that orange-lit plane, or somewhere in Robert Herrick's 30 years of patient waiting encoded in a changed vent on Maat Mons. If you did drift off, that is exactly as it should be. The story will still be here when you wake up. Venus will still be there, visible at the right time on the right morning or evening, holding its place in the sky. If you are still here, still listening in whatever quiet corner of the planet you have settled into, I hope there was something in this slow journey that felt worth the trip. Not the horror tour version, not the hellscape, melt you, acid rain, the end version that we have all heard. The other version, the twin that started like us and broke, not as a corpse, but as a living, volcanic, geologically active world still in the middle of its own story, with 3 spacecraft on their way to ask it questions it has been keeping to itself for 30 years. We are made of the same materials as Venus, the same elements, the same gravity, roughly the same distance from the same star. The difference between a world where you can fall asleep listening to someone talk about planets and a world that destroys titanium spacecraft in 2 hours is, in large part, where your carbon is. In the air or in the rock. In a runaway loop or in a slow cycle. In a furnace or in the limestone at the bottom of a warm, shallow sea. That is a small distinction, cosmically speaking, and it is everything, wherever you are tonight, in your bed, in a city, under a sky that might or might not be clear enough to show you that bright wandering light if you looked, you are inside the lucky outcome. You are on the twin that kept its water. And for now, at this moment, that is a good and quiet thing to carry with you into sleep. If you enjoyed this slow drift through our nearest celestial mystery, a gentle like or a subscribe means a great deal. Small creators like me genuinely rely on your support to keep these nights going. And do leave a comment telling me where you are watching from and what time it is in your corner of the world tonight. I read every one, and there is something lovely about knowing the geography of wherever this reaches. Until next time, sleep gently. Good night from up here in orbit. I'll keep watch while you drift.